Am I audible? Hello, am I audible?
Yes.
Yeah, is the screen visible to
Hello.
you? Is the screen visible to you? Uh, I'll share the screen. Is the screen visible to you? Can you like this? Okay, let me share again. Okay, hi. Welcome to the first lab session of Points of Topology 1. First, let me introduce myself. I'm Shovik, research scholar for IIT Madras, working with Dr. Ramesh Kashilingam. Right now, I am in the third year of the PhD and my area of interest topology. I am one of the TA of this Points Topology 1 course for this entire semester. This is going to a 12-week course, and there will be total 13. There will be total 13 live session. Okay, so the main objective of these live sessions are to problem solving and clearing doubts and discussing those assignments whose answer has already been released. Okay, so, but till now, but since today is the first day, and since Sir has done only up to nominal spaces like those things, so we can start doing assignments after 1 or 2 weeks. Okay. So in the meantime, we can first we can make us ourselves familiar by introducing ourselves. Why we need topology? Because there is something reanalysis matrix spaces there. So why the topology is important? That is the first question of our discussion. Okay. So once again. By the way, mm, over chat, I shared a Google form. Please submit the Google form in order to mark your attendance. So first question is, one second. Can everybody see the screen? I mean the screen. Sorry. So first question is why topology? So okay, so before starting, please tell me how many of you are from undergraduate and how many of you are from postgraduates? You can write in the chat box also. Okay, by the way, one thing I should mention is that while projecting the screen, I can't. Okay, your PG. Okay, good. What about others? There are total. How many students? Okay, there are Mr. Akshay, Mr. Clifford. Akshay Clifford, you are from PG or UG? You can write in chat also.
Where is the chat? I don't see the chat.
Okay, you can tell. No problem. Okay, okay, and Mr. Clifford, you are from undergraduate, postgraduate.
Uh, I have a I have a master's in mathematics,
Okay, that's great. That's great.
but I'm a lifelong learner,
Mhm.
and I'm just trying to. I love math. I'm just trying to learn some more math. Actually, I belong to this meetup group, and we're reading Hatcher's algebraic topology.
Okay.
But I've been wondering about the underlying point set topology underneath like the CW complexes and that kind of thing. So
Yeah.
what's the underlying, cellular homology? What's the underlying?
Mm.
point set topology. So, and I figured I'd take this course because I'm a little weak in topology and just like really, get it solid, you know. So
Okay. Oh, that's good to hear. Just I want to know one thing. So, what brings? I mean, so before joining this course, what you are doing? Like you are from industry background, you are from academic background. Just I want to know.
well, I was a software engineer. I'm retired. Um,
Okay, sir.
but I was a software, I did work in science and engineering
Mm.
the first half of my career at two different laboratories. I was a scientific programmer. But then I went over into the business side. But,
Mm.
I love math, since ninth grade. That's like my
That's good.
hobby.
Mm. It's good actually. I really appreciate this. Actually, it's very nice. Okay. So, one second. So first question is why we need to understand topology. Okay. So before going to the topology, there are some things like real analysis, metric space, non-linear space, or in short, it is NLS. Okay. So these are the things we already there in undergraduate, postgraduate course. So the first question is why what is the nature of topology? Okay. So the first thing is that the fundamental thing of reanalysis or metric space or the nominal space is that suppose we have 2 points, then we can measure the distance. In reanalysis, it is the Euclidean. In reanalysis mean in r to the power n. Sorry, it is r to the power n. In r to the power n, we have some coordinate geometry formula of measuring the distance between 2 points. Okay. In metric space, we have given some metric d with some space x, and that metric d gives serves the purpose of distance. And in NLS, we give some, suppose we have some norm given there, and then from that we can say that distance between 2 points is defined as norm of x minus y. So one of the fundamental point of this reanalysis up to metric space is that we can measure distance between 2 points. So the thing is, topology actually is quite, so topology is trying to generalize these things without introducing any metric or any distance type of tool. The thing is, in reanalysis, in metric space, non-linear space, after getting the distance formula, we have some notion of open set, closed set, closures, limit point, those things. In topology, we are defining, we have in the, in the topology we have some axioms, and based on the axiom we can define the closed set, open set, limit points, closure, etc. Okay. Now the thing is that there are some topology which can be induced from some metric, and some topology can be induced for some from some norm also. Okay. So in those cases, for example, in real line, there we can give some topology. In real line, there is a metric, namely the Euclidean metric. Okay. So in some situation, those the topology and the topology induced from the metric maybe coincide. In that case, we can say that that topology is induced from some metric. Okay, we will see these things soon, but this is the overall idea. Is that firstly we will start with some axiom. Okay. Then based on the axiom, we are going to define some open set, close the limit point, and then so on. Okay. But the thing is, topology starts with some axiom. This is the main thing. Now if one may ask why some axiom, but the thing is that in real analysis we have some distance formula, distance thing. In metric space we have also distance thing. In nominal space we have some distance, and using those things we can define the open set, closed set, and all. But in topology we don't have any distance concept. In topology we can only work with open set, closed set, and for that, we in order to define those open set, closed set, and all, we need to have some axioms, which is nothing but the sophisticated version of those distance function of reanalysis or the nominal space. Okay. So first let me write down the axioms of topology. I mean the definition of topology. In between, if some of you have any question, any doubt, please ask me by unmuting yourself, because while writing on the screen, I really can't see the chat actually. I mean, I need to switch the screen. So if you have any doubt, please unmute yourself and ask the question. Okay. So let me know the definition first. So suppose let X be a non-empty set and let tau, which is a subset of power set of X. Kindly wait a minute. I shall be back after 1 minute. Sorry. Yeah, sorry. So yeah. So suppose we have some space X. So no, sorry. Suppose we have some state X. X be a state. Okay. Right now we can't use the word space. Okay. Suppose X be any non-empty state and tau is a subset of power set of X. Okay. Then tau is said to be a topology on X if it satisfies the following. First of all is that the empty set phi and the whole set capital X must belong to tau. Second thing is that suppose Ey, I belongs to some index set, are elements of tau, then their union will also belong to tau. And the third axiom is, suppose, yeah, please tell me.
So, tau,
Yes,
I
yes.
mean, tau doesn't have to be the power set. It could just be a collection.
Yeah, that is the tau is a subset of power set. That's it's a subset, right? Yeah, it's a subset.
Okay, yeah.
Yeah, yeah.
Okay.
So suppose we have a tau, which is a power set of, which is subset of a power set of X and satisfy the following axiom. First of one is the empty set and the whole space belong to tau. Second thing is, suppose we have some arbitrary collection of Ey's, which are elements of tau, then their union is an element of tau. And the third one is, suppose if I is equal to 1 to n, these are the elements of tau. This implies intersection fi is an element of tau. Oh, sorry, one second. If tau satisfies these three following properties, uh, then we say that tau is a topology on X, and we say that X comma tau is a topological space. Okay, so this is a definition. So the thing is that so so analogous to the realized metric space, nominal space, if you consider those situations, so in, I mean, look, the thing is that the tau is defined in such a way that arbitrary union of some elements of itself lies inside it, and finite intersection of such element of itself lies within it. So, and in metric space in real there is one theorem that arbitrary union of open set is open, and finite intersection of closed set is closed, right? So, so I mean, this is the analogous statement, which we are going to take as a definition of topology. And anyway, in real and nominal space, null set and the whole space are the open sets. Okay, so so that's why we are going to take that thing here as a definition. And so this is a definition first. Okay, and X comma tau is called a topological space. Okay, so let's give some examples first. So, what I mean. So, first example is okay. So, so suppose we have some x, okay, and take tau to be power set of x. So this, so I mean, one second. Okay, so before going to this, there is some one thing I need to mention. Sorry. Hmm. So one thing is that definition. The elements of tau are said to be the elements of tau are said to be open set of X. This is the definition of open set in the topology. Okay? This is the first thing. This is one definition. And another definition is uh, if subset of X is said to be closed set if its complement is an open. F is said to be closed set if its complement is an open set. Okay, that is F complement belongs to tau. This is the first two definition of open set and closed set in the topology. So now let's go with some examples. So take X non-empty and take tau to with Px. Okay. So now says look that tau is Px. This implies what? This implies all subsets of X are open. I mean, of course, tau, if we take tau to be Px, then of course, this defines a topology. I mean, it is obvious. But the observe that if tau is, we are taking tau to be Px, so all subsets of X are open sets of X. So that's why this topology is said to be discrete topology. That is, everything is open. Similarly, if we take tau to be x comma phi only, then x comma tau is said to be indiscrete topology. Okay, so these are some trivial examples. Let's go with some non-trivial examples first. So okay, so we have seen matrix as nominal spaces. Now we are going to see that those nominal space or the matrix space define a topology. So how? Okay, once. So the thing is, any matrix space is a topological space. Okay, so how? So suppose XD be a matrix space. So what we need to do here? So as from the definition, I mean, first we need to somehow make the what is tau? Yeah, we need to somehow get this tau from D. Now the thing is, the tau is defined is nothing but in the case of matrices, we have to define the collection of all open set in the in X. Okay, so this is that tau we are going to take. So since X is a metric space, so there is already well defined notion of open set, closed set. Can anybody please tell what is the notion of open set and closed set inside a metric space? That is, U subset of X is open if and only. Can anybody please say? Anybody please?
Oh, if it's an open ball, uh,
Yeah,
without the bound.
yes, correct, correct. So if and only some, I mean, so if and only for any x belongs to U, there exists an epsilon greater than 0 such that the open ball around x contain inside U. This is the definition of open set. Okay. So the thing is that if we define tau to be U subset of x such that U open in x, then claim is that x tau is a topology. I mean, it has to be topology. This is our guess. We need to prove that our guess is right. So, in order to prove that, first what we need to do, I mean, what are the properties of tau? The properties of tau are firstly x and I mean the whole space and the empty set are the elements of tau. Means what? We need to show that whole set and the empty space are open set. Now, in metric space, of course, the whole set and empty set are open set, right? So that is phi and x belongs to tau. Okay. The second property is that suppose second property is what? Second property, yeah, arbitrary union of elements of ui is an elements of ui. Yeah, sorry, arbitrary elements of tau. Arbitrary union of elements of tau is an element of tau again. That is one need to show. Let ui be open in x. We need to show that union ui is open in x. So I mean the thing is that it is, I mean, it is an obvious result. I mean, it is a not obvious, sorry, it is a well-known result of matrix that the arbitrary union is open, and similarly, finite intersection of open set is open in X. So these are the well-known result of matrix space, arbitrary union and finite intersection of open sets are open. Okay, so that's why that axiom 2 and axiom 3 has been satisfied. So that's why this in a matrix space, the collection of all open set of capital X is a topology. Okay, this is one thing. So any matrix space is a topological space. Okay. So now, okay, this example tells that if we have some metric, then we can get some topology. But there are examples in which we will see, possibly it is not possible by today, but maybe after second or third class, we will see that there are some topological space which cannot be induced by any metric. For the time being, for the time being we will see some topological space, but right now we are not in the position to prove that whether a topological space is induced by some metric or not. Today we are going to see only some examples of the other topological space. Okay, so there is one example which is popularly known as cofinite topology. Uh, okay, can anybody please say in right now Sanskrit said is going through which portion? Is he going through a nonlinear space or has he started the topological space? Can anybody please confirm?
I have
Are
seen
you
a
at? Uh,
But please, you can also write down a chat also. I'm looking at the chat right now. Maybe there is an internet issue. Anybody please? Which portion is right now going in the success class? Okay, okay. Thanks, Jules.
Are you are you asking what the
Yeah.
cofinite
No, no,
topology
no,
is?
no, no. I'm just asking that in the successors class, which topic has been covered till now? I got the answer. Thanks, Jules. So, uh, one second.
By the whole
Okay,
week I will the all the lectures of the whole week. I just saw up to lecture three. I haven't seen the other lectures.
okay. Sir has done possibly the whole. Okay, so I mean, no problem. Sir has done actually nominal space. Then he will start the topological space. But the thing is, um, I mean, okay, no problem. Let's get some idea of the topology. Then we'll start with the nominal space because why in nominal space we need to only solve problems. There is nothing much to get inside of that theory. So that's why I started the topology today itself. Okay. Yeah, please.
Um, at some point, could you talk about metrizable?
Yes, sir. Sure, sure. Not
Because I
today.
can see,
Yes, yes. Not by today because right now we are not in the scope of that thing. Possibly after 1 month we will be in the position to talk about metrizable space because it is not just our definition. There are some criterion by which we can say that some space can be metrizable or not. Okay. So right now we
yeah,
can't say that thing. After 1 month we will get into that. Okay.
because I can see how a metric space has a topology, but
Yes, yes, yes.
I'm not clear on the other direction. If topological space could be metrizable.
Yes, correct.
So
Yeah,
I'm
yes, yes.
okay.
Yes, I mean
Okay.
we'll get into the definition by today. It's maybe, but we will not get into the criterion by which the sum space is metrizable or not. We will get into the definition itself. No problem.
Okay. Thank you.
Yeah,
Thank you.
yeah. So,
I'm just curious. Can I ask a question?
yes, yes,
Um, is there any way to differentiate between if there is a metric for a topology? If we find a topology, is there any way to find out if it was induced by a metric, or how could is there a way to find out a metric, something like that?
yes. That's what Mr. Kilford is asking. There is something known as metrizable space, and there is some criterion of some space to be metrizable. By metrizable, we mean that suppose we have some topological space. By metrizable, we mean that can we find some sorry, suppose we have some topological space. By metrizable we mean that can we get some topology by which that metric is I mean can you get some metric by which the topology is induced. So that is known as metrizability. Now the point is that there is some theorems or some lemmas through which we can decide that some given topological space can be induced by some metric or not. Okay, so that is the thing. And there is a straight cut theorem and answer for that, but right now we are not in the scope of giving that answer. Okay, so that's why please wait for 1 month because uh, in order to answer those questions, first we need to develop some technical tools. Okay, and those things comes under separation exams. So which is actually the last part of the points of topology. Well, not last, but it comes after 1 or 1.5 months in the topology course. So kindly wait for 1.5 months, then we'll get to know about those answers. Okay.
Thank you.
So there is one example known as cofinite topology. So how that is defined? Well, again, yeah, cofinite topology on a space X itself. By the way, in the meantime, let me tell clearly that if some of you know doubt, you can ask me, or also if there is some issue in understand handwriting itself, please ask. Okay. So the topology is defined as follows. It is known as cofinite. Okay, so so tau is all those u subset of x such that either x minus u is finite or whole of x. Okay, so this is definition. So all those subset u of x for which its complement is finite or x minus u is whole of x. Okay, so is the definition of cofinite topology. So I mean, it is at first glance it is not obvious that it is a topology. So let's check all those axioms are being satisfied or not. Okay. So first axiom is that we need to check the empty set and the whole space X is inside tau or not. Correct. So the thing is, oh sorry, one thing, cofinite topology on X and the space X itself is defined to be infinite, of course. Okay. So first question is that whether phi and empty set are inside the tau or not. Okay. So now thing is that x minus phi is whole of x. So this implies what? Phi belongs to tau. And x minus x is phi, which is a finite set. I mean, aqueously finite set. So this implies x belongs to tau. So the first axiom is being satisfied here. Second axiom is take an arbitrary collection of elements from lambda, sorry, from tau. So this implies what? This implies either x minus u are finite or whole of x. Okay. Now we need to show that their union is inside tau. Okay. How to show this? So we need to somehow check that x minus union ui, these things are finite or not, or it is whole of x or not. Anyone which is any whatever is possible. Okay. So the thing is, I mean, observe that this thing x minus union of ui is nothing but intersection of x minus ui, right? And which is anyway subset of x minus ui for all I. Okay. Now observe one thing that we have taken ui from tau itself. So either sum of x minus ui is finite or everything or it is whole of x. Okay. So if we assume that if we assume that at least for one I x minus ui is finite. So assume that there exists I naught such that x minus u I naught is finite. So then this implies what? This implies intersection I x minus ui subset of x minus u I naught, which is a finite set. This implies what? This implies x minus of union ui is a finite set. So this implies union ui belongs to tau. So if we, so by our choice, we have two options, x minus ui are finite or each of them whole of x. If at least one of x minus ui is finite, then we can see that this whole union ui belongs to tau. Now for the second situation, if x minus ui is equal to x for all I, this implies what? This implies ui is equal to 5 for all I, and this implies what? This tells what? This tells union ui is nothing but phi itself, which of course belongs to tau, right? So whatever the case we are taking, the arbitrary union of ui's is an element of tau. Okay, so that's the thing. So here we only need to use the two fact that, two cases. First of all, either x minus ui is finite or it is whole of x. If we consider that at least one of x minus ui is finite, then we can check that union of ui is an element of tau. If all of x minus uy is whole of x, then their union is empty. So anyway, it is an element of tau. Okay. So the axiom 2 is being satisfied. Okay. Now consider the axiom 3. That is, let ui I is equal to 1 to n is an element of tau. We need to check that a finite intersection is an element of tau. So since this thing are element of tau, this implies what? X minus uy is finite or all of x. Now the thing is, so first we need to check this complement x minus intersection uy. This is equal to union of x minus uy. Okay, I is equal to 1 to n. Now observe that if all of x minus uy are finite, then their union is finite. So if all x minus uy is finite, this implies their union is finite. Okay, because observe that we have only two possibilities, either all x minus u are finite or sum of them all of x. So here we have used that all x minus u are finite. So in that case, that finite intersection is an element of tau. Okay. Now, but if some for some I x minus uy is equal to whole of x, that is uy is equal to empty, so I mean, then what? Then intersection uy is equal to empty set, which is trivially belongs to tau, right? So in both the for both the cases, either x minus uy is finite or x minus uy is all of x, we get that intersection of uy is an element of tau. So that's how the third axiom of a space of a set to be topological space is being satisfied. So that's why here whatever we have defined as tau is a topology on x. Okay, and this topology is known as cofinite topology. Okay. Okay, one thing is note that it is cofinite topology is not metrizable. I mean, cofinite topology cannot be induced from any metric. But but we will see the proof after a month possibly. Okay, right now keep in mind. Similar to the cofinite topology, there is one thing known as okay okay. So there is one name of cofinite topology named as finite complement topology. So it is one of the synonym. So similar to cofinite topology, there is one another topology named as co-countable topology. So let X be an uncountable set, and we are defining tau to be U subset of X such that X minus U is countable or whole of X. Similar to the proof of the cofinite topology, here also you can check that this forms this satisfies all actions 1 2 3. Okay, we are not going to check here, you can try yourself. If you are getting any difficulty, please ask me in the next live session. Okay, right now we are not going to proof here because this proof is exactly same as the proof of the cofinite topology itself. Okay, so yeah, So this is okay. And once again, we check the what's the next thing. Okay. Okay. So now there is one concept known as the basis of a topology. No, sorry, there are two things. It's my mistake. So there are two things. First is that basis, and second thing is that basis for a topology. So they, I mean, they are almost same, but there is slight difference. So first of all, let me tell why the name basis is here. So in the vector space, we have some well-defined concept of basis that which is nothing but like any element can be written as the linear combination of those basis elements, right? In the metric space, you must have seen one theorem that any open set can be written as arbitrary union of open balls, right? This is the one theorem that is any open set can be written as arbitrary union of open balls. Right? This is another thing. So the thing is, since I mean due to this reason, in metric space, bx epsilon, this type of thing can be considered to be a basis in the metric space. But well, let me first define the basis in the mathematical form. So the definition of basis. Let Okay, first thing is that in order to define basis, it is not necessary to have a topology. We can define a basis direct from the given space. Sorry, I mean directly from the given set. So let X be non-empty set. It is a set. And let beta be a subset of a power set of X. That beta is a collection of some subsets of X. Okay. Then beta is said to be a basis of X if the following are satisfied. If for every X belongs to X, there exists a beta X belongs to beta such that X belongs to beta X. This is the first axiom. Second axiom is that if X belongs to B1 intersection B2, where B1, B2 are basis elements, then there exists then there exists another basis element inside capital B such that B3 subset of B1 intersection B2. If these two conditions are being satisfied, then we call the space capital B to be the basis of capital X. Okay. Now, the thing is that observe that these two conditions is obviously being satisfied in case of metric space, nominal space analysis, right? So in topology, basically we are defining things in such a way that those are analogous to some results or some lemmas which we usually prove in metric space or reanalysis. Here we are going to take those things as our definition or as our action. Okay, in this way actually this thing works. So okay, so this is a definition of basis. We'll see some examples, but there are some definitions on the track. So there is one definition, namely topology generated by basis. So first there is a concept of basis. Like in vectors, we have some basis, and using that basis we can define. I mean, using that set we can consider vector space of which that set is can be treated as a basis element. In topology, we can do something like suppose beta be a basis of x, and we are defining tau to be all those subsets u of x such that for every x belongs to u, there exists beta x inside the basis. There exists a beta x inside capital B such that x belongs to beta x, which is contained inside u. Okay, and one can check that this gives a topology on x. Okay, and this topology x tau is said to be topology generated by the basis beta. Okay, this is topology generated by beta. So this is one thing, and next and second thing is that elements of beta are called basis elements. Okay, so this is another definition. I mean, yeah, this is a basis element. So this is all regarding basis and the base topology generated by a basis. Okay, and there is a reverse concept known as this is the thing basis for a topology. So here we have seen that we have some basis and we are going to define a topology using that basis. Now there is one fact or theorem or a definition also you can say that suppose we have some topology and we can get some basis which generates the topology. Okay, but we'll see that definition soon. So let's give some example first. One second. Okay, so suppose consider what? So take x to be non-empty and define beta to be all singleton x of, I mean all singleton subset of x. Now it is, I mean first of all, since beta contains all singleton elements, so anyway beta satisfies that axiom 1 and 2 obviously, right? So beta is a basis. Sorry. And what is the topology generated by beta? Beta we are taking to be the all singleton subsets of, I mean singletons of capital X, and clearly beta is the basis. I mean it's obvious. Now the question is, what is the topology? Sorry, generated by beta. Can anybody please say? So whatever the topology we are going to get from beta, in that topology, all singletons of capital X are going to open. From this, can anybody please guess what is the topology we are getting from beta? I mean, it is obvious that, I mean, from the definition of topology generated by basis beta, it is obvious that whatever the topology we are going to generate, the elements of beta belongs to tau, right? So each of elements, each base element is going to open in that generated topology. So in our example, we have chosen beta to be all singleton set. Now we want to know what is the topology generated by that basis capital B. So whatever the topology is, in the topology, all singletons are going to be open. Now from this, can anybody please guess what will be the topology generated by the beta itself? Anybody please guess? Think about it, you can take your time. Okay. Correct. Discrete. Just now I've said it. Yeah, good. So that is the discrete topology. Okay. So uh, let's go to the next example. So let X be a metric space, and we are defining beta to be the all open balls. Now it is, it is quite evident that this forms a basis. Why? Because for any x we can get in open ball of radius epsilon, and if we take two open balls, if we have any element x inside two open balls, then if we take that x, then we can take a small radius, we can take open ball here. So this forms a basis for, so in metric space, collection of all open balls forms a basis. Okay. I'm not writing the proof, but for whoever is new to subject, please write a detailed proof by yourself. Okay, because writing is extremely important for the exam purpose. Okay. So in metric space, this is from the basis, and obviously the topology is generated by the basis is nothing but the metric topology that we have seen in the metric space itself. Okay, so we are not getting into that discussion because metric space is a separate course. Okay, so one second. Okay, so now one second. Okay, so there is one thing we need to keep in mind. So look, sorry. Suppose we have some two topology tau and tau dash on a given space capital X. Now the thing is how to check that those tau and tau dash are same. How to check those topologies are the same. So look, we start from the definition. Tau and tau dash is nothing but the subset of a power set of X. So we need to show that if we take any element from tau, that is any element which is open in tau, that has to be open in tau dash, and conversely if we can show that any element that is open in tau dash is open in tau also, then tau and tau dash is same. Okay, it is obvious, but it is important to keep in mind. So that is u belongs to tau if and only if u belongs to tau dash. That is u open in u belongs to tau means u open in x tau if and only if u open in x tau. Okay, so there are two another concept, namely one second. Yeah, so there are two definitions. Let tau and tau be two topologies on X. Okay. Then we say that tau is finer than tau dash if tau dash is subset of tau and tau is coarser than tau dash if tau subset of tau dash. Okay, sorry, yeah, correct. So tau is finer. Finer means what? It is, I mean, tau is finer means in tau there are many number of open sets in tau compared to tau dash. So in that sense, tau is said to finer. If the finer is in that sense that there are many number of open sets, it is fine in that sense. So tau is finer if tau dash is tau and coarser if the tau is tau dash. Okay. So in terms of is the definition in topology. Okay. Suppose we have the following situation. Suppose beta generates tau and beta dash generates tau dash. So in that case, of course, in order to check tau and tau dash are fine or not, we can go with the definition one. We can check one or two. Okay, but that's definition. But in order to check it quickly, of course, there is some theorem. As you might guess. So the theorem is as follows. One second. So theorem is that tau dash is finer than tau if and only if for all x belongs to x and for all bx belongs to beta with containing x, there exists beta dash x containing beta such that, inside beta dash, such that x belongs to beta dash x subset of beta x. Okay, so this is a theorem. So what is the theorem states? Tau dash is a subset of tau. Sorry, tau dash is a superset. This any set which is open in tau is also open in tau dash. Okay, so the thing is, it just holds if and only if you take any x and if you take any beta x. Okay, now the thing is, this beta x has to be open in tau. Okay, so by definition of topology generated by basis, this implies what? We will get some element beta dash x inside beta dash such that this whole beta dash x contained inside beta x. Okay, this comes directly from the definition of topology generated by basis. So that's why it is obvious, but you need to keep in mind. So let me repeat again. So suppose it is given that tau is a subset of tau dash. Okay, so we need to check this following instruments holds or not. So we take any beta dash and beta x which contains some x. Now this beta x belongs to beta, which of course belongs to tau. So this beta x is open in tau, but it's given that tau is a subset of tau dash. This means what? This beta x is an element of tau dash, means this beta x is open in tau dash, means there exists an beta dash x containing x, sorry, beta dash containing x, such that this beta dash x is contained inside beta x. Okay, so this is the one way. And other way goes as or goes similarly according to the definition. So other way, so proof of other way, I'm not going to write it down. You can try yourself the proof of the converse part. It is very easy. It is directly comes from the, it directly comes from definition itself. Okay, please try yourself. If you get any difficulty, you can ask in the next live session. Okay, so this is one criteria of some topology which is finer or worse in the given one. Okay. Yeah, please.
How is this theorem? How is that different from the definition?
Yeah, it is not different from definition, but thing is, while working with problem, we it is not always possible to first generate the topology, then we need to check whether tau is a subset of tau dash or not. Okay, so that's why this theorem is important. It is not actually different from definition, but I think while working problem only it is important, otherwise it is not that much important. Okay, both are essentially same, of course. Okay, so okay, I shall be back for after 2 minutes. Okay, so one second. Okay, so okay, so after defining the basis, there are some examples actually regarding that thing. So the first example is the following. What is that? Okay, sorry. So first example is that um, so let beta be the collection of all open intervals in R. That is, it consists of all open AB. A belongs to R, A less than B belongs to R. And of course, I mean, I mean, the topology generated by this basis beta is known as standard topology. I mean, the name is obvious what is standard. Okay. Similarly, inside Rn also, if we define the open sets, then topology generated by those open sets is known will be considered the standard topology. I mean, standard is considered the underlying situation. So that's the standard. Okay. So there is another topology named as lower limit topology. This topology is defined entirely in terms of basis. Okay. So lower limit topology on where? On real line R. Okay. So we are taking capital B to be closed A, open B. This forms a basis first. I mean, I'm not going to check that. It is quite obvious from definition itself. This forms a basis, and the topology generated by this basis is called lower limit topology. Okay, and there is another thing. I mean, of course, since there is a concept of lower limit is left side third bracket and right side first bracket. So, of course, there is analogously there is something known as the upper limit topology, which I am not going to write. It is, I mean, the thing only it is open a closed B. That's all. Rest everything is same. This is the upper limit topology. Okay, and there is another topology uh, known as um, K topology. Okay, so how it is defined? In this case, we are taking beta to be all those usual open intervals inside R K topology on R real line. Okay, union open AB minus A, where AB belongs to R, of course, where the set K is the 1/2, 1/3, dot 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 1 by n dot dot dot. Okay, this is the set capital K. Okay, so this forms a basis on R. Okay, and it is not strict. I mean, it is not difficult to check. I hope you can check it by yourself. I am not writing the proof because these things come directly from definitions somehow. Okay, please check these things by yourself. If you get any difficulty, please ask me in the next session. Okay, so these things, and this is known as the K topology. Okay, and it is denoted as R suffix K, where K is the set. This. Okay, now, okay, so we have defined something known as standard topology, lower limit topology, upper limit topology, and K topology. Okay, so first, I mean, so some of this topology actually does not come from any metric. We will see this thing after some months. But right now we are going to check whether this topology. I mean, okay. So okay, one thing I missed is that lower limit topology is denoted by R suffix L, and the standard topology is denoted by R suffix U. U denotes the usual word. Okay, I mean usual topology. That's all. Okay. Now, um, there is okay. So there is one thing. There's one theorem actually. The thing is the usual topology is sorry, not usual. The lower limit topology RL and K topology RK are both finer than R with usual topology, okay? But they are not comparable, okay? So this is one theorem actually. I mean this type of thing. I mean the thing is that it will not definitely come into the exam, but in order to understand or in order to get some intuitive feeling topology, we need to understand these things. Okay. So
What do you mean by comparable, not comparable?
oh sorry. Yeah, sorry. Compatible means sorry. One second. So I mean, suppose we have some topology tau and tau dash on X. Okay, they are said to be comparable if either tau is a subset of tau dash or tau dash is a subset of tau. Okay, this is by what we mean a comparable. Understand? I mean, this is the definition. Sorry, I missed actually.
Okay.
Sorry.
Okay, thank you.
So not compatible means we need to say that none of, I mean, each are none of can lie inside other. That's all. So first of all, we need to check that RL or RK are both finer than RU. So what we need to check is that the usual topology is a subset of RL and the usual topology is a subset of RK. Okay, means that the open sets, not just R. Okay, of course, this is the way of writing. So okay, so now the thing is that RL, RK, I mean lower limit topology and the K topology has been defined in terms of basis. Okay, so in order to check that whether RU is a finer quartz than RL, we need to check this. We need to use this following definition. I mean, so we need to use the following theorem. That is this portion, this theorem. So,
Excuse me, I'm sorry.
yes, yes.
Is this shouldn't here it should be beta x is a subset of beta prime x or beta dash x. Shouldn't be the or
No, no, no.
reverse.
Yeah, no, no, no. It is. The thing is that here tau is a subset of tau dash. So here in terms of beta, it will get reversed because the thing is what? If tau is a subset of tau dash, this means what? I mean, any open set in tau is also an open in beta dash, right? Sorry, in open in tau dash. And here beta dash x subset of beta x means what? This beta x is an open set of tau dash. So that's why beta dash x subset of tau dash here makes sense. Understand?
I'm sorry, could you please repeat your
Yes,
argument?
sure, sure, sure.
Hurry.
Tau, yeah, no problem. Tau is a subset of tau dash means what? Any open set of tau is an element of tau dash. Means
Yeah.
any open set of tau is open in tau dash. Now we are taking beta x. Beta x is open in tau. So beta x has to be open in tau dash. Now beta
Yeah.
x is open in tau dash means what? We need to get some basis element around x inside beta x and which lies between beta dash such that beta dash x subset of beta x.
Okay. Maybe I
Okay,
need
yeah, I mean,
some more time. I'm
let me
sorry.
show the definition. Wait one second. Yeah. So here is the definition of topology generated by basis. Means what? We have some basis. We have some open set tau. For every open set x belongs to u, beta x belongs to beta such that x belongs to beta x subset of u, where u is a set in capital X. So this means what? If we consider tau to be topology generated by beta, means if we take any open set and if we take any point from the open set, we will get some beta x inside beta such that that lies entirely in U. Okay.
Okay.
So there's a
Yeah, now
definition.
I get it.
Yeah, good.
Now I get it. Thank you. Thanks a
Yeah.
lot.
So here we need to check that what is that? Sorry. We need to check that this relation holds or not here. Okay. So what we will do? We will simply take an basis elements here. What are the basis elements? Base elements of the form open AB. These are the base elements in RU. Okay. Now we need to check that if we take one, I mean, if we need a single base element, if we take any point from the basis element, we need to get that there exists some. I mean, the thing is, we need to put some base element inside open AB, which is actually basis element of RL. So I mean, so if we take any C here, so I mean x belongs to open AB, this implies what? X is greater than A. We can take any C here. So this implies what? X belongs to third bracket C comma B subset of open AB. Actually, it does actually we can write X belongs to third bracket X comma B, which is subset of open AB. Okay, and is an this element is an basis element of RL. Okay, understand? So I mean, so that's why that theorem regarding some basis, that's why that theorem which connects the compatibility of some topology with the basis elements is important. By using directly this, we can say that these two topology are finite or not. Okay, understand? So that's all it is. So what we have done, so first we took an open set from, first we took an open AB from RU, and we take any element x from open AB, and now we somehow got some elements which is the basis elements of the lower limit topology inside AB. Okay, so that's why RU is a subset of RL. Okay, so this is one thing. So this is one side. Second side is we need to check that RU subset of RK. Now the point is that what are the basis element of RK? The basis elements of RK are this. So these are the basis element of RK, where the usual base element of R is there, some plus some extra. So of course, I mean, any basis element, so I mean, so any basis element of RU is also an basis element of RK. So of course, RU subset of RK holds trivially. Okay. So what we have seen till now, R usual is a subset of R with lower limit topology, and it is also a subset of R with K topology. But the interesting thing is that it is a subset. It cannot be an equality. Okay, I mean it is a proper subset. So for this, what we need to check, this is what we also need to show that lower limit topology, I mean usual topology is strictly coarser, or we can say in language that RL and RK are strictly finer than RU. Okay. So this is the thing. You need to, I mean in language this is the thing. So how to check that? So for that, what we need to do? We need to check, obviously we need to check, we need to find some open set in RL which cannot be open in RU. Okay. So how to do this? To get an open set in RL, not open in RU. Okay. So, what we can take in some open set. So, for example, look. So, thing is, suppose we consider any A, which is an element of closed AB. Okay. This is an element. Now we need to check that this is not an open area. So we need to check closed AB is not in open in RU. So this means what? So this means what? I mean, something is not open. How we can show? I mean, how to say this? So it's suppose in metric space. Okay, suppose F is a subset of some matrix XD, and suppose we need to show that F is not open. Then what we will do? Can you please tell how to show that something is not open? What to do? Anybody please? Any? Can you please, anybody, whatever the you have the idea, please tell how to show in some metric space, or forget metric space, in real line. I mean, in case of real analysis, how to show that some set is not open. Don't
If
please,
to
yeah.
check if the boundary points are included.
Sorry, the boundary points. Please tell boundary points. I can't hear you properly actually.
Sorry, to check if the boundary points are included in the.
Boundary points. Okay, okay. So I mean, well, that's one definition, but we have some definition of open set itself, right? Like if you take any point, then we can get some open interval lies inside the given set. Okay. So in terms of that definition, can you please negate the statement? That is, suppose suppose you have given some set and how to show that in, I mean, the set is a subset of R. How to show that that is not open subset of R? I mean, directly from definition, how we can show. Yeah, Crystal. Directly from definition, how we can show. Okay, so thing is that in case of real and symmetrics, whatever. Suppose f is a not open means what? So it means that there exists some x inside f such that um, there does not exist any open ball containing x lies inside f, right? So the same thing we are going to check in the topology, that is in lower limit topology, the set closed A open is open, but we are going to check that this is not open in usual topology. It is obvious in usual topology, the open interval is open. This thing cannot be open, but we are now going to check in terms of definition of topology itself. Okay, so first we need to choose a point around which we cannot find any open set which lies inside closed AB. We need to check that. So in from the picture it is clear that if we take the point a capital small a, and if we take the open interval around small a, then of course whatever the small open interval we can take around a, that interval cannot lie inside closed AB, right? So that's why none of the base element of lower limit topology cannot be is open in usual topology. So what is the idea? We took any basis element, we take the extreme left point, and if we take any basis element containing small a, that basis element cannot lie entirely inside closed AB. Okay, so that is why closed AB is not open in R with usual topology. Okay, so that's the argument. So that's why R with usual topology is a proper subset of R with lower limit topology. Now let's check that R usual topology is a proper subset of R K topology. Okay, by the way, let me tell one thing that this argument might seem to be slightly complicated, but the thing is, this argument is exactly same as how we can show some set to be not open in case of matrices or in case of reanalysis. The same way we have to here, but only difference is that in case of topology, we have some predefined notion of open set base element. That's the only thing we have used here. We have not used any other extra thing. Okay. If you have any issue understanding, first sit with this thing for first 15-10 minutes. Then also, if you then use issue, then please ask me in the next live session. Okay. But but the thing is, this thing can be this thing directly comes from the definition itself only. Okay. Okay, so now let's show that R with usual topology is the proper subset. It's proper subset R with K topology. So this means what? First we need to take some open set, which is first we need to take some open set inside Rk, and we need to first choose some point from that open set. Okay, so consider the open set -1, -k. This thing is open in R with K topology. Okay. So thing is that in R with K topology, base element contains of this type of thing plus this type is open A minus K. So that's why any element of this type is open in R with K topology. Okay. So here it is -1, 1, and here we have some elements of K. These are the excluded part. And suppose 0 is an element of -1 to -K. Okay. Now here we have 0. Okay. Now suppose 0 belongs to open AB, which lies inside -1, 1 minus k. So this implies we have some open intervals containing 0, and this open interval lies inside -1 to minus k. But such a thing is not possible because any open interval containing 0 will contain some elements of the form 1 by n due to Archimedean property, right? I mean, yeah, from Archimedean property directly we can say that if any open interval contains 0, it will contain some n naught, but according to the definition, open AB has to be lie inside -1 minus capital K, and capital K contains the point 1 by n naught itself. So that's why such a thing is not possible. So such a thing is not possible. One second. What happened? So yeah. So one second. Sorry, there's some issue. Came with the screen. Can you see the screen?
Yes.
Okay. Sorry for the interruption. Yeah. So basically, yeah. Okay. So this 0 belongs to open AV, subset of -1 minus k. If such a thing is going to happen, this implies what? This implies this, due to argument property, 0 belongs to open AV. This implies what? Some 1 by n naught belongs to open AV. But the thing is, since open interval a comma b has to lie inside -1 minus k, and this set capital K contains 1 by n naught, so such a thing is not possible, right? So this implies what? This open interval -1 minus k is not open in R with R with usual topology. Okay, it is not open. So that is why RU is proper subset of R with K topology. Okay, so this is the argument. So is the argument clear to everyone? I mean, it is quite
Yeah.
tricky. Okay, okay. So now, okay, so till now what we have shown is the following, that RU and, I mean, the usual topology, sorry, the lower limit topology and the K topology are strictly finer than the usual topology. Now we are going to show that they are not comparable. They are not comparable. That is, we somehow need to show that uh, none of them can be subset of each other. That is, RL is not a subset of RK, and RK not a subset of RL. This is what we need to show. First, please try by yourself for some minutes. In the meantime, I shall back. Okay, but please try. I shall back after some minutes. So now we are going to show that let me go to chat actually. Mm. Clifford, can you please unmute yourself and please speak again? What's your doubt? Actually, I could not figure out your doubt. Actually, please unmute yourself.
I'm sorry, what was that?
Yeah, I mean, please tell the doubt. Actually, I could not figure out your doubt from the chat itself. Yeah, please tell your doubt. I mean, unmute yourself and tell the doubt. Okay. No, so what you have written is that so we have written that minus 1 comma 1 is open in R with lower limit topology you have written, right? But the thing is that I mean minus 1 comma 1 cannot be open in R with lower limit topology because R with lower limit topology, what are the base element? Base element of the form closed openly, right? So if you consider minus 1 comma 1 to be open here, and if you consider this point 1 itself, so any open set containing 1 will look like what? Third bracket x comma y, but x is less than equal to 1, but y is strictly greater than 1. And in such a case, this third bracket x comma y, sorry, third bracket x, first bracket y, cannot lie inside minus 1 comma 1, obviously, right? So minus 1 comma 1 is not open in R with lower limit topology. Okay, you understand?
Yeah, did I get that backwards?
Sorry.
Did I get that
Yeah.
statement backwards? Like, did I get it the wrong way around?
And your next question was is okay. Zero.
So,
Okay, so you have written that third bracket 0, first bracket 1 is inside R with K topology. So open in R with K topology open. So how to so the first thing is that what is the base element of R with K topology? The base elements either of the form open AB or of the form open AB minus K. So now the thing is that so here open the third bracket I close 0 open 1, okay, and if we take the point 0 here, and if this is open in R with K topology, so either 0 belongs to some open AB which lies inside 0 1, or 0 belongs to open AB minus K which lies inside 0 comma 1. So but the thing is that I mean, of course, such a thing, I mean, this is not also possible and this is also not possible, right? So closed 0 comma 1 is actually not open in R with K topology. We have written one second. Yeah, open. Yeah, correct. That. yes, right. Open 0, comma 1. It is open in R with K topology, not in R with lower limit topology. Okay. So yeah, you're right. And what about the converse? I was mm, yes, correct. So yes, correct. So as per your mentioned in chat, close 0, comma 1 is open in R with lower limit topology, but not open in R with K topology. Okay. So yeah, so that's why the lower limit topology and K topology are not comparable. Okay, this is one of the important thing. So okay, yeah. So there is one second. There is mm, there is one example exercise whatever, but take it as an example also. So there is one example. So take x to be r and define beta to be open AB such that A less than B and AB belongs to rational. Okay. So now, so it is, I mean, first of all, check that beta is a basis and which is quite obvious. So I'm not going to check that. But thing is, second question is that, look here AB belongs to rational. Okay. Uh, okay. So first is beta the basis and the topology generated by beta and prove that topology generated by beta is usual topology on R. That is if we, I mean, if we consider the only open intervals having rational endpoints, then the topology generated by that is nothing but the usual topology, and which this is also actually quite obvious because if we take open AB, which are both rationals, then those axioms is being satisfied, which we can easily see. But the thing is that this thing satisfy only with the usual topology. Okay, but um, yeah, but if we define another collection C, I mean, okay, so I mean, this example has nothing to do. I mean, this is quite obvious. There is no need to mention, but actually there are some other examples that we are going to see now. That's why I have mentioned this example only. Okay, so there is another example. Take X to be R and C to be closed A open B, A B belongs to R, A B belongs to Q, rationals. Firstly thing is that this is a basis. It is quite obvious to check, but the thing is that topology in previous example we have seen that the topology generated by base elements have a rational endpoint is the usual topology, but in case of if the base element is take to be closed open we are AB are rational, then topology generated by C is different from lower limit topology on R. Okay, so that is the interesting thing. If we take consider the extreme intervals to be rationals, a rational point, then the topology will be different. Okay. So how to check that? So we need to check that. So what we need to check? We need to take some open set, which is sorry. We need to take some set which is open in the topology generated by C, but that is not open in the lower limit topology. So consider, or we can consider the vice versa also. Okay. So consider the interval third bracket root 2 comma first bracket 3, and consider the take root 2 inside that. So this thing is open in R with lower limit topology, but this is not open in. So call this topology generated by C to be tau C. So this thing is not open in tau C, we need to show. Okay. So here is the interval root 2 3. Suppose if it is open, if it is open in tau C, this implies what? This implies root 2 will lie in some open AB which lies inside root 2 comma 3, where this open A, this points A and B comes from the rational number. But this equation gives what? This equation gives that A is equal to root 2. But this is not possible because A comes from the rational. Okay. So that is why this set third bracket root 2 open interval 3 is not open in tau C. So that is why the topology generated by this C is entirely different from the lower limit topology or real line. So this is one thing one may keep in mind. Okay. So one second. Okay. So there is some. Okay, so there is one theorem which is actually similar with the metric space. The theorem goes as follows. So in metric space, what we have seen? In metric space, we have seen that topology, sorry, in metric space, we have seen that any open set can be written as arbitrary union of open balls, right? In topology also, we will see that any open set can be written as arbitrary union of best element. Okay. So let X tau be a topology or topological space. Then any open state of X can be written as arbitrary union of basis elements. Okay. So how to do? I mean, it is not difficult, but it strictly comes from definition. And and of course, sorry, I forgot to mention one thing: topological space with basis beta. Okay, that's all. So for mention. So take U be open in X. Then for every X belongs to U, there is beta X subset of B such that X belongs to beta X subset of U. And this implies what? This implies U is equal to union of beta X. X belongs to U. I mean, so this is what it is. Okay. So, I mean, that's why it is very much obvious. And that's why this capital B is called as basis. Okay. So, so this is one thing. And okay, so there is one exercise actually. I think it's better to think about the exercise whenever you're free. So the exercise is follows. Suppose x is a no x is an infinite set. No, once again. Suppose x is an infinite set. Then comes the collection tau infinity. U says that x minus u infinite or empty or all of x. Question is, is it a topology? So you need to check that whether those conditions are being satisfied or not. Okay. Please think about it. I mean, you can take your time. Please think about it in the class itself. Okay. What is the question? X is an infinite set. We have defined something known as tau infinity, which contains u such that x minus u is infinite or empty or all of x. Now the question is tau infinity forms the topology of that? Okay. So please try it. And if you get your answer, please let me know. Yes, Clifford. Yes, Mr. Clifford. Tau with Q has a counter basis. So I mean, so what? I mean, yes. So what? I mean, I don't get it actually. I mean, there are some theorems regarding counter basis and all, but in this connection of this example, I don't think there is any connection with tau with a counter basis. Ah, okay, okay. No, no, that. Huh? No, 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 no. It is not just tau. It is one second. Hmm. So this collect this collection, yeah, this collection C is a basis. Okay, for basis we call the definition, we don't require the whole space X or we don't require the empty set to be inside capital B. there are only two axioms for a set to be basis, and we need to check only that two axioms and being satisfied or not. That's it. Okay, there is no point of considering other things. Okay, so this is a basis, and here we are considering topology generated by that basis, and we need to check that is different from the lower level topology. Okay, that's it. Okay, so this question we have figured out.
It is a topology.
How?
Because if we take u to be phi, x minus phi will give x, and so it is a part of the topology. And if we take u to be x, we will get a empty set, so it is a part of the topology. And since x is infinite, if uh, uh, I, since x is infinite, if the union of I'm sorry.
That's no problem. The thing is, I mean, first of all, the thing is, it is not a topology. Okay, so you need to find the count. You need to find some example with infinite x, and you need to come up with some use for union or the intersection that axiom is not being satisfied. Okay, it is not a topology, so you need to somehow come with some
Okay.
counterexample. I mean, it is not difficult. Think about it. It is not difficult at all.
Okay. Sorry.
No problem. Okay. So today is, yeah, it is going to 9 p.m. something. So let's stop here. So if you have any doubt, you can ask. Or one thing is that please mark your attendance by submitting the Google form that I have pinned in the chat actually. Yeah, I've sent that Google form again in the chat. Please everybody mark your attendance. Please mark your attendance. Did everybody mark attendance or
Yeah,
submitted?
I did.
Okay, okay, thank you. Okay, okay, thanks, Mr. Clifford. Okay, thanks. That's for the today. We'll meet in the next Friday, same time, 7 to 9. And also, if you have some doubt from today's session, you can email or you can ask me directly in the next live session. Okay, thank you. So I am leaving the call now.
Thank you.